In this video, we're going to discuss the distinction between a population and a sample from a statistical standpoint, and we're going to discuss some of the basic parameters that describe a population. First, let's talk about the difference between a sample and the population. The population consists of all possible outcomes for a random variable. For example, if you're doing a survey of voter preferences, the population would be all voters. If you're trying to characterize the population of college students, the relevant population would be all college students. In practice, when we're engaging in statistics, though, we generally don't have access to all the data in the population. We don't really need all that. What we work with is a sample, and a sample is just a subset of the population. We use information from that sample, specifically sample statistics, to try to infer the characteristics of the population. Most probability density functions and cumulative density functions are described by a small number of population parameters. If you think back to your statistics course, the normal distribution is characterized by only two, the mean and the variance. When we work with samples, we generally try to draw random samples of the population so that it's representative of the population as a whole. If you don't do that, you may end up with estimates that do not reflect the overall population. And we'll go through many examples of that in this class. One of the most basic characteristics of a population is the population mean, and that's also written as just the expected value of the random variable. And in the case of a discrete random variable, it's defined to be just the sum of all the outcomes times the probability of observing those outcomes. So if there are n possible outcomes from x1 through xn, you take each of those, you weight it by the probability of observing that, and you add them together, and that weighted average tells you the mean, which we typically express as mu sub x. And that represents a weighted average of all the outcomes, which reflects the average value of that variable in the population as a whole. In the case of a continuous random variable, we need to use a little bit of calculus. In this course, you won't be required to use calculus, but for those who are already familiar with it, the population mean is defined to be the integral of the variable times the probability of observing that times dx from negative infinity to positive infinity. And essentially, this is just a continuous analog of the way in which we compute the mean in the case of a discrete random variable. Let's take an example to illustrate the concept of expected value. Many of you have participated in 50-50 lotteries that are often used as fundraising tools for clubs and organizations. And in the case of a 50-50 lottery, tickets are sold often at $1 a piece, and half the money goes to whoever wins the lottery, and half of it stays with the organization. Let's look at the two possible outcomes that would occur from the standpoint of a buyer. If there's 100 tickets sold at $1 each, there are two outcomes. The most likely outcome is that you'll lose, and in that case, you've lost $1. So we're measuring X as the change in your income by participating in this lottery. 99 out of 100 times, you will lose $1. 1 out of 100 times, though, you will gain $49. And the reason it's $49 and not $50 is you have to pay that dollar to participate. So either you're going to lose $1 99% of the time, or you'll come out ahead by $49, which would happen 1 out of 100 times. Now, if you're watching this on YouTube, I'd suggest you pause the video and try to calculate what the expected value is. So now let's compute that expected value. We take each outcome, we weight it by the probability of observing it, and in that case we get the value of -1 times 99 out of 100, which is x times f of x, plus 49 times 1/100th. And when we do that, we get a -99 plus 49 in the numerator, 100 in the denominator, which becomes a -50 over 100, or a loss of 50 cents. So on average, every time you spend $1 participating in a 50-50 lottery, you're going to lose 50 cents, which makes sense since half of the money is going to the organization that sponsors the lottery. Now, one concept that you've heard is the law of large numbers. And what the law of large numbers states is that the observed frequency of an outcome converges to the population probability as the size of the sample approaches infinity. What that means in practice is that as your sample gets arbitrarily large, the frequency observing it should converge to the population frequency. So what this means basically, in large samples, the sampling distribution that we observe will tend to look very much like the distribution of outcomes in the population as a whole. Now, there are certain properties of expectation that's going to be useful for some of the things we'll be doing later in the course. A proof of all of these is contained in the textbook. The first is that if C is any constant, the expected value of the constant is that value itself. If C is equal to 100, it's going to be 100 no matter what happens in the state of the world because it's a constant. So constants are the same no matter what happens to any random event. If X is a random variable, though, and A is a constant, the expected value of A times X is equal to A times the expected value of X. Since this is being recorded in upstate New York, let's say you're shipping apples, and the apple has a random weight based on the size and shape of the apple. The weight of that apple could be defined to be the variable X. What this is saying is that the expected value of, say, 2 apples would be equal to 2 times the average weight of an apple. If you're going to ship 20 apples, the average weight of shipping 20 apples would simply be 20 times the average weight of an apple. So the expected value of a constant times a random variable is always equal to that constant times the expected value of X. Property 3 essentially combines property 2 and 1, and it states that if A is a random variable and B is a constant and X again is a random variable, the expected value of AX plus B is equal to A times the expected value of X plus B. Now, to help see that, we can again take that example of shipping apples, but now let's say we're going to ship those apples in an actual box. And let's suppose that the boxes are very precisely made so that the weights are, for our purposes, a constant. So let's suppose we're shipping A apples, where X is, again, the weight of an apple, which is a random variable, and B is the constant, which is the weight of the box. So the expected value of the weight of that whole package would be equal to the number of apples you ship times the average weight of an apple plus the weight of the box. We can also know that if X and Y are random variables, the expected value of the sum of the variables is equal to the sum of the expectations. In upstate New York, 2 of the major crops are apples and onions, and I'm not sure why you'd want to ship them, but let's suppose X is again the weight of an average apple and Y is the weight of an average onion. Let's suppose you want to ship an apple and an onion to someone. This tells you that the expected value of the combined weight would be equal to the average weight of an apple plus the average weight of an onion. More generally, combining those first 4 properties, we can demonstrate that if X and Y are random variables and A, B, and C are constants, the expected value of AX plus BY plus C is equal to A times the expected value of X plus B times the expected value of Y plus C. So essentially, this just combines what we've talked about before. Another way of putting that is that the expected value operator is a linear operator. One last property of expectations. If X and Y are 2 independent random variables, the expected value of the product of X and Y is equal to the product of their expectations. This may not be quite as intuitive, but a proof of that is contained in the textbook. But we should be clear on what we mean by independence of random variables. 2 variables are said to be independent if the distribution of each is unaffected by the level of the other variable. So if the distribution function for X is the same no matter what happens to the level Y and vice versa, then this condition will hold, that the expected value of the product is the product of the expected values. We should note, though, that the expected value of g of x will not generally be equal to g of the expected value of x. For example, the expected value of the variable x squared is not the same as the square of the expected value of x. And a proof of that is contained in the textbook. We should also, though, talk about the variance and the standard deviation. Earlier I mentioned that the two characteristics of a normal distribution are the mean of the distribution and the variance of the distribution. We define the population variance, which is normally written as sigma squared, as the expected value of the quantity x minus mu sub x squared. So if we look just at the term within that expected value, that's the deviation of x from its mean. And we're looking at the average squared deviation of x from its mean. In the case of a discrete random variable, we measure that by taking each of the possible outcomes, finding its deviation from the mean and squaring it, and then weighting that by the probability of observing it. There is an analogous definition for a continuous random variable. But essentially what we're doing in either case is we're trying to find the average squared deviation of the variable from its mean. One thing you should recall from your statistics class is that when a distribution has a smaller variance, it's more tightly bunched together. The tails thin out more quickly. If it has a larger variance, it has more dispersion. So essentially, the variance is a measure of the degree of dispersion in the underlying distribution. So with a small variance, the observations tend to be more tightly clustered. With a larger variance, the observations tend to be more widely dispersed. Here's a numeric example, which actually appears in your textbook too. But let's just go over it briefly to see how we can compute the variance if we know the outcomes and their probabilities. If you engage in a single roll of a fair die, there are, again, 6 possible outcomes, 1 through 6. The average value of those will be 3.5. And you get that by just taking 1 times 1/6 plus 2 times 1/6 and so forth. And we end up with 3.5 as the average of all those possible outcomes. We form first the deviation of x from its mean for each of those outcomes. So 1 minus 3.5 is a negative 2.5, and so forth down that third column. Then we take those deviations and we square them, which is given now in the fourth column in this table. So when we square a negative 2.5, we get 6.25. Now, we multiply each of those square deviations by the probability of observing it, and that's what appears in the last column in this table. And then to measure the variance, we just add up all those square deviations weighted by their probabilities, and we end up with 17.5 times 1/6, or 2.9167. So the average square deviation of the outcome of a single roll of a die from its mean would be 2.9167. The standard deviation is a concept that you also worked with quite a bit in your stats class, and the standard deviation is nothing more than the square root of the variance for the distribution. There's a few properties of the variance that you should be familiar with. The first is that we can also express the variance of a random variable as the expected value of x squared minus mu sub x squared. That can be fairly easily shown with a little bit of algebra, and again, that is done in the text if you're not comfortable with this or if you don't recall this from when you first studied introductory statistics. Second property, and this is one that people often get confused by, is that if x is a random variable and a is a constant, the variance of ax is equal to a squared times the variance of x. And when students are given problems with this, the most common mistake is to assume that, well, the expected value of ax is equal to a times the expected value of x and assume that something similar is true of the variance. That's not true. Remember, the variance is a measure of the expected value of the squared deviations. So if we look at the variable a times x now, you scaled everything up by a factor of a. The mean of ax would now be a times the mean of x. But when we square those deviations of ax from its mean, you're going to end up with a squared times the square deviation of x from its mean. And when we simplify that and pull that a squared out, we end up simply with a squared times the variance of x. And again, you could work through the algebra on that and see that, but just remember that if you multiply a random variable by any constant, and you want to find the variance of this new variable, it's always going to be that constant squared times the original variance. The last property of variance that we're going to use now is that if x is a random variable and c is a constant, the variance of x plus that constant will equal the variance of x. And the reason is fairly simple when you think about it. If x increases by a given amount, so will the mean of x. And all those deviations will be exactly the same when you look at x minus its mean or x plus its constant from its mean, because the mean shifts up or down for this new variable by exactly the same amount. And as a result, whenever you add a constant to a random variable, the variance of that new variable is going to be exactly the same as it was before, as long as you don't rescale the variable itself. Just simply shifting it up or down will not affect the variance of that distribution.